All right, so the previous couple days we've talked about rotating sigma bonds and alkanes, but then we finished up talking about bicyclic and monocyclic ring systems. So the question is, if you have things in a ring system, can they rotate freely or can they flop around in space? And as you guys can probably tell, the answer is yes, because we have a whole section on it. So let's talk about the different ways we can draw cyclohexane in particular, because it's one of the most common monocyclic ring systems you'll encounter. There's three ways you can consider drawing it. All right, so let's take a look at the first one. This is our bond line structure for cyclohexane. This one's nice and easy, right? If we think about cyclohexane, 6 carbons in a ring system, right? Arguably the easiest way to draw it. However, let's imagine I'm looking down this bond and I'm looking down this bond, right? We can do a double Newman projection down both of those parallel bonds. So if you have your model kit, what I recommend doing is make a cyclohexane ring. And then what you want to do is hold it in front of you like this so that you can kind of look down both of those bonds. You guys see what I'm kind of showing you? So 2D, we've got our cyclohexane, and then lay it on its side and look down 2 parallel bonds. One of the carbons should be kind of puckered down in the back or front, while the other one should be opposite. You guys kind of see that? So it looks like a diamond when you look through it. Okay, so let's draw that Newman projection. So when you do that, it looks a little bit weird. But those are kind of your front carbons that you're looking down, right? So if we think about it, this position right here is a CH2 that is puckered down. CH2, right? Because it's in between. Okay, and then let's focus on those back carbons. And then in these back carbons, you can imagine this one in the back is puckered up. And then last but not least, we've got these hydrogens over here. And I'm just going to make these solid lines because we know they're in the back now. And then we've got hydrogens pointed down as well. Does that make sense if you have your model kit? Right? Looking down at one of them is going to be puckered up, the other one's going to be puckered down. All right, so that's another way you can draw it. To be honest, not a lot of people draw it this way because you can probably tell it takes a lot of work. So that's the Newman view. That's essentially our side-on view as opposed to the top-down view. And then there's one last one called the chair conformation. And the chair conformation isn't a top-down view. It's not a side-on view. It's actually kind of looking at it from an angle. And so the way people typically draw this looks like this. And I'm going to draw in all of the hydrogens. Don't worry, we're going to practice drawing these. And then we've got a hydrogen in the back right there, and a hydrogen out like that. So this is kind of our side-on angle view of what's going on here. So does that make sense? Top down, straight side-on, and then angle side-on. That's why I have a video. So let's take a look at this video here. So that's Newman. That's the chair. Whoop. Oh, I need to loop it. So top down, Newman, chair. Let's do it one more time. I need to figure out how to loop this. So that's top down. We'll do it a bunch of times till we get sick of it. Top down, Newman, chair. You can watch this for hours on a loop, right? It's kind of cathartic. This is why a model kit's really handy, right? If you've got a model kit, you can look at the Newman and then kind of angle it on its side, and that's the chair. So top down, Newman, and then chair is kind of tilted on its side a little bit. Does that make sense? I know a lot of people, they've got what looks like this with 2 carbons pointed up, right? This is actually another conformation called a boat. So that ideally you want 1 carbon up, the other carbon down. So what we'll do is we'll practice drawing these because I know it's super confusing, and then we'll come back to the video. All right, so let's talk about how to draw a chair. All right, and I'll explain why people call it a chair too at the end. All right, so the first one is draw offset parallel lines at approximately 60-degree angles. It doesn't need to be perfect, obviously. What it really means is you've got one line angled up like that, and then another line right below it angled like that. Make sense? That's the starting point. All right, and then step 2 is draw triangle connectors. Above and below to connect. Okay, so if we look at the top ones, I'm going to just replicate them like this down here. What I mean by that is we've got a triangle right here. Whoop. Does that make sense? That blue triangle, that one's kind of puckered down. And then the other triangle, oh, let me fix this a little bit, is kind of puckered up like that. Does that make sense? Now here's where I show you how the chair name developed. Imagine this as like a little hinge right here, and that is a little hinge right there. You can imagine laying out on a beach on this, right? So this is your headrest. And down here, this portion of the triangle we'll call our footrest. Does that make sense? Those dashed lines are just imaginary hinges where you can actually flip your headrest down and your footrest up, just like a normal lawn chair. The other thing that's important is you want to make sure that everything is parallel at this point, right? So for example, I told you those first set of lines should be parallel to one another. And then these lines out here should be parallel to one another if you're good at drawing. And then same with these ones. They should all be parallel to one another. All right? So now what we need to do is we need to start adding substituents to this chair conformer, right? So let's do a whole section on where to put our substituents. All right, so let's copy this chair that we just drew, and I'll kind of break it down. We'll do add bonds straight up for carbons pointing up. So if I redo my chair down here, that's my attempt at a chair. First thing we've got to do is identify the carbons that are pointed up, right? So if I look at this carbon, it's pointed up. What about that one? Looks like it's pointed down to me, so we're not going to do that one. Next carbon pointing up is this one. This one's kind of pointed down, so we don't include it. This one's pointed up, and that one's pointed down. So the ones with red dots are pointed up carbons. And what I'm going to do is I'm going to just draw straight up and down lines for each of these. You can tell that red carbon in the very bottom is kind of offset, so that line going through it is actually in front of everything else. So I'm just going to label these with A's. And that's that, right? So those substituents just go straight up and down off of your chair. All right, and then number 2 is add bonds straight up and down, or I should say straight down, for carbons pointing down. Okay, so let's try to redraw this real quick. So we already had these groups up here pointed up, so I'll draw in all of these positions. But now if we want to identify carbons pointing down, it's basically going to be those other carbons, right? So for example, this carbon, I'll draw a bond straight down, this one straight down. This one in the back, you can tell it's behind it, right? So you can have that slightly broken line to show that perspective. And again, I'm just going to label these with A's. But they're perfectly straight up and down. If you look at my model kit that I'm holding up right now, can you guys see that those are all green? They're going directly up and down. Ideally, when you make your chair, you can color code them, right? So I just color coded all my up and down ones green. All right, now what we need to do is fill in the remaining ones, and these are a little bit trickier. And then we said add remaining substituents so that they are parallel to adjacent CC bonds. So I'll show you guys how to do this, but let's copy our chair that we just did and then we'll add it all back in. You guys thought this was a chemistry class. You didn't know it was art. There we go. Oh yeah. I want it to be Picasso-esque. Actually, please don't do Picasso. It's hard to tell. All right, so that's what we had before, right? I'm going to keep that line tight. There we go. So we've got all our up and down substituents. Now I'll show you what I'm kind of looking for. So you see this bond right here that I'm highlighting in blue? This carbon over here with the blue dot will have a substituent coming off of it that is parallel to that. So do you see how they're in line with one another? So I'm going to label this B. Or actually, let's do E, and I'll show you why. Okay, so we'll do that one. Let's pick another one. So you see this blue line right there on the lower portion? That means we need a parallel line coming off of this position, and we'll also label that E. So both of those are kind of pointed towards one another. All right, now let's do the left-hand side. So I'm going to change colors a little bit. So we've got this orange one right there. That means over here we must have a parallel position, also with E. And then over here we've got this orange one. And again, that's going to be parallel to that position right there. Can you guys see how they're kind of lined up as parallel pairs? All right, now what we've got to do is the remaining ones, and these are a little bit tricky. So let me change colors a little bit. We've got this bond right here in red. That means this position must be parallel to that, and I'm going to label that as an E. And then the remaining bond over here is pointed that way. So I'm going to draw this bond parallel to that, also with an E, but it's behind. Does that make sense? It takes a lot of practice to get good drawing these. I'm not going to be super duper picky, but what I do like students to do is to label their substituents. So what I'm going to do real quick is I'm just going to erase these, redo them as black. That way we're not completely overwhelmed by color here. And I'm going to do all of the ones going out as E's. And all of these positions that are sticking straight up and down that I labeled with A, they're called axial, right? Because an axis is typically going straight up and down. You can imagine the Earth's axes. And then the ones kind of sticking out and away from the ring, these are called equatorial. So quite often on exams and quizzes, because I know it's tough to draw these, I'll say do your best attempt at drawing them, but more importantly, label them as axial and equatorial. That way I know what you're trying to represent it as. Make sense? So that's the typical chair structure, but I want to show you something unique about these chairs. This is something special they can do called a chair flip. So if you get tired at drawing these, you can flip your chair over in anger. It's a joke. Not a good one. All right, so I'm just going to draw a really simple chair with two substituents coming off of it, right? So I'll just pick substituent coming off there. Is that going to be axial or equatorial? Axial. Axial, okay. So I'm going to just label that A. And then we have another substituent coming off kind of this direction, and I'll call this B. What I like to do is to identify those chair hinges, right? So where your headrest is and where your footrest is, and kind of do a dotted line. Those are our chair hinges. I like drawing them in. You don't have to, but I really like to. And then what you're going to imagine doing, you're going to take this footrest and you're going to flip your footrest up. And you're going to take this headrest that we talked about and you're going to pull that headrest down. All right? And this can occur at room temperature for a lot of cyclohexanes, but when you do this, now the two parallel lines that you start with are offset in the opposite direction. And you see how that headrest on the left is now pointed down? So I'll put my dotted line in there. So I pulled that the headrest down. It's going to be our new footrest, which means our footrest, if we imagine this hinge right here, is actually going to be up in this position. Okay? So now the question is, we've got these two substituents coming off right there. Do you think A is going to be sticking straight up and down, or do you think it's going to be pointed out and away? Out and away. So A is actually going to be located right here, while where B is located straight up and down. Does that make sense, pulling that headrest up? Or pulling the headrest down and the footrest up? All right, that's the weird thing, is during a chair flip, your axial substituents become equatorial, and vice versa. So anything that was axial becomes equatorial, anything that was equatorial becomes axial. All right. For those of you that have model kits, what I want you to do is to color code all your axial ones with the same color, and then if you have different colors, color code those as your equatorial. Does that make sense? Can everybody kind of see my chair? So axial's green straight up and down. I'm going to turn on some lights. Then I'll show you this. Grab 2 carbons on opposite ends. So for example, this one right here is the headrest. Can you see how it's pointed up? The one in my other hand is my footrest.
Yep.
So what I'm going to do is pull my headrest down, and then I'm going to pull my footrest up. And that's a chair flip. So you see how everything is yellow? Those are my axial ones. But when I do the flip, I pull it up and down. Now green is axial. It's kind of weird to imagine it that way. So try it a few times. So if you pull your headrest down and then footrest up, you complete your chair flip. It's a little bit weird to think about, but when you go through these conformational twists, you go through a couple different stages. The first one's kind of a halfway twist, where it's like that. This is referred to as twist. And then if you pull it all the way up, can you guys see how this is kind of a boat shape? And then you pull the other one down a little bit, halfway. You go back through twist, and then down back to a new chair. Personally, in this class, I'm always going to ask you about chair conformations, not twists or boats, because those are energetically a lot less stable, but you may run into problems in the textbook or on sapling where it uses those terms. So twist is halfway between a footrest being pulled up, and then when you pull it all the way up, now you're in boat, and then you pull your headrest down, you go back through twist, and then back to your chair. That's why these model kits are super handy, is you want to practice doing this a few times to get good at it. Does that make sense? Okay, so let me dim the lights again, and then we'll continue on. So what I want us to do is to practice interconverting between a two-dimensional structure to a chair. So going from 2D to chair. All right, so let's start with this compound. I'm going to put a methyl group up on that position and down on this position, and I'm just going to label them as CH3s, right? Now what we need to do is name this. How are we going to name it?
Cyclohexane, multi-methyl cyclohexane, 1, 2.
I'm hearing a lot of answers. What's the longest ring system here? What would the parent ring be? It's a hexane, it's cyclic, so it's cyclohexane. Then we want to number it. So I'll just go around this way. So this would be 1, 2, dimethyl cyclohexane. And then there's one last thing we need to consider, right? I could have drawn that methyl group off of carbon 2 as a wedge. I drew it as a dash. Does anybody know what we call things that are opposite of one another in chemistry? Think about alkenes. Cis and trans, right? Would this be cis or trans if they're on opposite sides? Trans. So oftentimes to show that relative position, we say this would be trans 1,2-dimethyl cyclohexane. And we'll talk more about that when we get into stereochemistry. Okay, so we've got that. Now what I want us to do is to practice drawing a chair, and then we're going to do a chair flip. Okay, so let's just pick one chair. And what I like to do is number my chairs. So again, because this is my chair, I can number it any way I like. I'll just go 1, 2, 3, 4, 5, 6. The important thing with this is you see how the one on the left I numbered going clockwise? That means on my chair I should also number going clockwise. You want to be consistent. Okay, and then with carbon number 1 on my chair, I've got an axial substituent sticking straight up because that's a carbon pointed up. And then out here I've got my equatorial substituent sticking out like that. Same thing with carbon 2. I've got an axial substituent going straight up and down like this, and then an equatorial one over there. Oh. So I'll put my numbers in. That's 1 and then 2. Now what we need to do is think about this chair. So what I like to do is imagine looking straight up and down on it, right? So that would have been bad. Imagine looking straight up and down on it like this, on top of your chair. So that's my little eyeball looking straight up and down. And if we imagine the methyl group on carbon 1, will it be closer to our eye or further away from our eye? Closer. So should it be axial or equatorial? Is it going to be sticking straight up or out and away? Straight up, right? If it's pointed close to your eye, it's going to be sticking straight up. So I'll put this CH3 right here. That means the assumed hydrogen on carbon 1 must be equatorial, right? All right, now let's think about carbon 2. All right, the methyl group in this case is now going to be further away from your eye. So is it going to be axial or equatorial? Axial, right? Because in this case, the furthest away position is going to be pointed straight down. That means the assumed hydrogen on carbon 2 is going to be like that in the equatorial position. This throws people because they say, well, carbon 1, you drew it as a wedge, but carbon 2 is a dash. How can they both be axial? It all has to do with the perspective that you're looking at the molecule at.
I was going to ask, why would it be trans then?
Yeah. Yeah, so that's a great question. You see how this methyl group off of carbon 1 is closer to your eye, so it's on the top face, where this methyl group is on the bottom face.
Yeah.
Because they're on opposite faces, they're called trans.
Okay.
Cis would be if they're on the same face.
I see.
Yeah. All right, so now what we need to do is we need to do our imaginary chair flip.
So then if the CH3 and the H got flipped, somehow if
So if, are you asking if carbon 2, if we had that as a wedge?
well, like the other CH3 went the same, somehow got flipped in the same direction, then they'd be cis.
Yeah, so for example, with carbon 2, if I switch that from a dash to a wedge, we would move this CH3 to this CH, or where the H is, and then they would be cis to one another. Yeah. I think it's easier to determine cis and trans when looking at the 2D structure. Cis means they're going to be the same, right? So both wedges or both dashes. Trans means they're going to be opposite. It's as simple as that, and I think that's the easiest way to do it. Okay, so now let's do the chair flip. Again, I'm going to do little hinges here. So carbon 1 to carbon 3 is a hinge. Carbon 6 to carbon 4 is a hinge. And carbon 2 in this case is going to be our imaginary footrest. So I'm going to pull this footrest up. And then carbon 5 is our headrest, so I'm going to pull that headrest down. And again, I need to draw offset parallel lines, but this time pointed the opposite direction. And you can kind of imagine my hinges are still there. But now the footrest that was on the right-hand side is a headrest pointed up. And the headrest that was on the left-hand side is now a footrest pointed down. What we need to do is number it, right? So if we look at the compound on the left, our footrest was carbon 2. That's now our headrest. So I'm going to say, all right, that old footrest is our headrest, so that's 2. If we go clockwise around the ring, this will go 2, 3, 4, 5, 6, and then 7. Oh, 1. There we go. All right. So if we think about carbon 1, we should have an axial substituent. And that axial substituent, because it's a carbon pointed down, should be pointed down like that. And then we should also have an equatorial substituent. So I'll draw that equatorial substituent kind of out and away like that. And then with carbon 2, we should also have an axial substituent right here, and then an equatorial substituent pointed out and away. So again, this is carbon 1, that's carbon 2. All right, for the time being, let's focus on carbon 1. Should the methyl group be axial, meaning pointed down, or should be out and away? Equatorial, out and away. So I'm going to just draw in the CH3 back here. Oh, that's tough. I'm going to redraw it like this. H3. Ugh, I don't like it. There we go. So now that's out and away. That means this hydrogen must be occupying that axial position for carbon 1. All right, carbon 2, will the methyl group be axial or equatorial? Equatorial. So I'll plug it into this out and away position, not the straight up and down one. And then the hydrogen will be right there. Does that make sense? All right, so if you have a model kit, this would be a great time to pull it out. So I'm just going to pull all my substituents off.
How come carbon 1 moved?
It all has to do with how you're viewing it, from what angle. So I'll show you guys how to view this in a model kit form. I know this doesn't work well for YouTube videos, but... All right, so that's my chair. Can everybody see that? Back here, I'll put the carbon straight up and down because we know that's equatorial. So can you guys see that? And then down here, I'll put this one down like that. Do we agree that's trans? It's a little hard to see. But the methyl group, one of them's on the bottom, one's on the top, so they're trans. All right, and I'm taking this footrest in my right hand, and I'm going to fold this up, and then my headrest over here in my left hand, I'm going to fold that down. And then if we take this over here, you see how this methyl group is now pointed back into the board? And then this methyl group is out and away. And then if you want to go backwards, you can say, all right, I'm going to take this headrest in my right hand, I'm going to pull this down, and take the footrest in my left hand, pull it up, and then I'm back to the starting chair. It's a little bit hard to see. I really recommend when you're doing these problems to practice with the model kit. Doing the chair flips with the model kit is when things start to really click. And it is tricky drawing these. If you notice on the pod, I give you a skeleton structure for the basic cyclohexane, and then I want you to plug in substituents. Quite often on exams, I'll do that as well to make things a little easier. All right, so now the major question is, which of these is more stable and why? This is a little tricky. The chair is always going to be more stable, but we have two different chair conformations. So the question is, do methyl groups prefer to be sticking straight up and down in the axial position, or do they prefer to be out and away, and why? All right, I'll show you guys something. So I'm going to plug in some assumed hydrogens that are also axial. So this was the same model kit. I just plugged in some imaginary hydrogens that are also axial. This is for the one where the methyl groups are also axial. Do we agree on that? All right, so this methyl group is going to spin around like a helicopter blade because we know sigma bonds can rotate, but it's in pretty close proximity to these methyl groups. If we do a chair flip, on the other hand, all of a sudden the methyl groups are pointed out and away, and they're not going to run into things that are nearby. So anytime you've got a big bulky group, it prefers to occupy the equatorial position over the axial. It prefers to be pointed out and away from everything else that's going on in the molecule. And I'll show you guys what this is called.
That doesn't change even though the two methyl groups be closer together.
Yeah, so what this is referred to as a 1,3 diaxial interaction, and those are destabilizing for large substituents. So what I mean by that is, let's draw the axial positions coming off here and then here. This methyl group is close in space to those two axial protons. So this is a destabilizing 1,3 diaxial interaction. The one on the right, the methyl groups are pointed out and away from the ring system, so it's not going to be running into other axial things, right? If we do the one on the left, or sorry, the other methyl group, you can imagine we've got two hydrogens right here and here pointed up and down, and these are destabilizing. That's a good question. Does anybody have an idea for why it's called 1,3? Has to do with the relative positioning of axial groups, right? They're never going to be next door to one another, but they will be one neighbor further than that. So it's just saying they're 3 carbons apart. So 1,3 means 3 carbons apart. Sometimes people just say diaxial because it's assumed that it's a 1,3 interaction. So typically big bulky groups prefer to avoid those 1,3 diaxial interactions, and you can identify the more stable structure. So for example, this one is more stable because there is no 1,3 diaxial interactions for the methyls. And again, this is kind of like Gauss conformations, where the interaction corresponds to the size of those groups. So the larger they are, the more they prefer to be equatorial. So for example, if you've got a tert-butyl group, that very rarely wants to be axial. It almost always wants to be equatorial. Does that make sense? You guys look a little mentally exhausted. All right, I think we'll call it there. If you guys want, you can hang out here for a few minutes and take a look at the pod. The pod is really similar to what we've been doing today and yesterday. Tomorrow, what we're going to do is a short in-class cyclohexane activity, so bring your model kit. We'll go over any questions you have. And in addition to that, I already posted the practice exam, which is last year's exam. You're welcome to go through it. Ignore anything that talks about optical activity or stereochemistry. We haven't learned that yet. And then Friday, during our study session, we can go over anything you want, and then I'll record and post the exam key as well.
You mean last year's exam 1?
Last year, exam 1, yeah.
Okay.
Behind.